Hello everyone and welcome back to ECS 2200. So let's go ahead and get started with our chapter 5, which is going to be on the operational amplifiers or OpAmps. So in this lecture we're going to talk about OpAmps. We're going to introduce them, talk about a little bit about motivation, what are the OpAmps, what are integrated circuits, which OpAmps are an example of them. And then we're going to move on to like basically talking a little bit about the ideal op amp and how what are the rules of analyzing circuits that involve an op amp. And then in the end, we're going to solve a bunch of examples of circuits that have op amps, and we're going to learn how to analyze them. Okay, so unlike the resistors and voltage sources and well later capacitors and inductors that you might have seen them or basically heard about them or even learned some stuff about them in the past, op amps or integrated circuits are not really that familiar to you guys, I can imagine. So before actually starting to talk about them, let's see why we need to actually talk about them and what are these things. So if you imagine any kind of electronic system, this electronic system could be your the main board of your computer. It could be if you turn on your cell phone and then see the main board that connects everything together, or any other electronic system that you can imagine. When you break it down, you're going to see things that are called printed circuit boards, right? So, for example, in this case, I'm showing this little headband, right? So this headband is something that you can even if you go to Best Buy today, you can actually purchase it for I don't know $100 or $200. It's a toy. It's kind of like a hobby toy, but it's also a little bit of a scientific device. So it actually, well, the manufacturers claim that they can record your brain signals from your forehead and using some electrodes that they put, basically a few electrodes that they put under this little plastic thing that touches the skin. They can pick up the brain signals and then they can actually help you meditate or help you have a better sleep. We don't care too much about the application. If you're interested, you can go and read it. But somebody actually has tried to tear this down and try to see what's inside. So if you are more interested in the details, you can go to this address. So if you open up this plastic encasing, you're going to see that other than the plastic stuff that are used for encapsulation, you're going to see that there's some connections, and the most important components or the most important modules in this system are two little green boards here. Of course, you have a battery to power the whole thing. But if we look at these two boards here, if you magnify them and look at them, these are the things, these green boards are called printed circuit boards, right? So these are printed circuit boards. And you might have seen these in different colors everywhere pretty much, right? So when I talked about the computer main board or your cell phone main board, all of them are printed circuit boards. Basically, it means that you have a board that basically it's made of a material called FR4. Could be a different material, but then it has a bunch of wirings. So like basically all the wires that we draw in our circuits are kind of printed on this board, and it might actually have one layer or two layer or like 30 layers, right? You can see some of these wires. If you look carefully, you can see some of these wires on the top layer here, but you might have more of these wires inside, right? And then all the components are somehow assembled on top of this board. So like some of you might have been hobbyists, and you might have played with boards such as Raspberry Pi. If you haven't, you will in the embedded systems course. But these components, so the Raspberry Pis are basically another example of these kind of PCBs, right? So if you look at these PCBs, this one here or the one on the other, like the bottom one, what you see is that there are a bunch of components. Some of them are just connectors, like this one is just a mini USB connector. But then some of them we already know. For example, these little things that you see here. Oops, I probably better to use a red color. So these little components that you see here are all resistors and capacitors, right? But in addition to these, you also have some components like these ones, right? These are the ones that we call them integrated circuits, or ICs in short, right? So when somebody talks about a chip or an IC, they actually mean something like this. right? So one of the most popular ICs that you might actually come across, and you're going to see it in pretty much 90% of different kind of boards and electronic systems, are amplifiers. And the most common amplifier that you might actually use is an operational amplifier or an op-amp. In this case, this is an op-amp in this electronic system. Okay, so just to give you an idea of what we are going to be discussing in this lecture is to learn a little bit about the most popular integrated circuit that you might find, other than like basically these passive components, so like these resistors and capacitors, right? Or maybe like sometimes inductors. These are the passive components. And then we might have some active components, the integrated circuits. And the most popular one of them is OpAmps. So it's nice to actually, if you are passing a course in circuits, it's nice to actually get introduced to such a thing and then learn how to analyze a circuit that includes an op-amp. Okay, but what are these ICs are made of? What's inside? Well, it's an integrated circuit made of sometimes tens, sometimes hundreds, sometimes thousands, or even millions of transistors. It's outside of the scope of this course. So if you're interested in that line of science and engineering and research, EECS 2210, which some of you will take next semester, is the introduction to that world. So here's a closer look at one of these ICs. So like if what you see on those mini PCBs is something like this. So it has a plastic kind of a case, and it has a bunch of legs or pins that basically connect the rest of the circuit to this little component, right? So if you kind of scratch off the plastic or ceramic cap, depending on, well, what component you buy, you're gonna see something inside. So here's the picture inside. So like the ceramic cap is actually scratched off. And you can see that these legs that we saw on top are actually connected somehow using these little narrow wires to something in the middle. That's the chip. So that is the integrated circuit. So the whole black thing that is around it is just basically some sort of a packaging thing. So you could package this in many different shapes, and that's why ICs come in different kind of package, different shapes and well, sizes, right? But well, the actual chip, the core is actually here, right? Why do we need this kind of packaging? Because well, this thing has millions of transistors in it, and there's no way that we can actually connect a wire to them, like to each and every one of them. So we have to actually take the inputs and outputs, bring them out, and then connect them to these little from these little narrow wires. We have to connect them to these big pieces of metal that come out and become one of these pins that we connect them to the rest of our circuit on the board, right? So what's inside of this chip? As I said, millions of transistors. So this is a picture, well, it's more of a cartoon of what is happening inside the chip. So you're gonna have like several layers of different kind of routings, and then at the bottom you have transistors implemented, and all of these are connected to each other. So right now, like people are actually fabricating transistors in this scale of nanometers, well, a few nanometers. So you can imagine that in a chip that is like, I don't know, a few millimeters by a few millimeters, you can imagine that how many thousands or millions of transistors you might actually have. So this is what basically made our lives different in the past few decades. This is the reason that we have today. We have computers and like any other kind of electronic kind of a gadget, let's say cell phone, GPS, whatnot, right? So everything that you can think of it today, from your TVs or your laptops or whatever you see in front of you that can be called an electronic device, it's basically made of these little transistors. Okay, so as I said, in this course, we're not going to get into the details of internal circuits of an integrated circuit. We're not going to get into the details of internal circuits of an operational amplifier, but we're going to deal with it as a black box. So as I mentioned here, we will discuss the terminal behavior and not the internal circuit. So you might, if you go to the lab, you might actually find different kind of op-amp packagings. So this is one of the typical ones. You can see that it has like 4 pins on one side and 4 pin on the other side. This cartoon is kind of like showing it from the bottom view, and you can see that it has different kind of basically terminals or like the signals at different pin that we're going to talk about each and every one of them. Okay, so we're going to deal with this component as a black box, similar to resistors. So when you talk about the resistor, you just show it like this, right? You don't care about what's going on inside, right? We didn't talk about how a resistor is built. The same we do with the capacitor, same we do with an inductor, right? We have an idea about how this is built from physics, but in this circuit analysis, we only treat this as a black box. We only treat this as a component that we are not really interested in what's going on inside. We care about what is happening outside. So for a resistor, for example, the only thing that we care about is that V is equal to R, I for a resistor that is equal to R, and for an I and V that are defined this way, right? For capacitor and inductor, we're going to talk about them after the midterm. Now we want to talk about an op-amp and basically how to model an ideal op-amp. So the symbol that we use for an op-amp is just a simple triangle. So most of the time we just show it like this, plus minus. We always have, we always have two inputs and one output, right? But if you look at these examples here, it actually has 5 terminals. So we have a positive input or the non-inverting input, and we have a negative input, or we call it inverting input. We have an output, and then we have two other terminals as well that sometimes we show them, sometimes we don't, right? If you don't show them, it doesn't mean that they're not there. They're there. We just implicitly assume that, well, it's there, right? What are these things? It's basically positive power supply and negative power supply. What do they mean? Well, like any other electronic component, if you expect an electronics device to operate for you, like let's say your TV, you expect the TV to work, meaning that if you just press a button and go to the next channel, you expect the TV to display the content of that channel to you. So for the TV to actually do that, it has to actually receive the signals from an antenna or like your cable, bring in the signals, interpret them, and then basically try to display them, basically decode the signals and then display them in a way that it's basically understandable by the display unit in the TV, and then, well, you're going to watch whatever is displayed, right? So for all of those functionalities to happen, there is one little but very important condition, and that is, well, you have to plug in your TV, right? It has to be connected to electricity. It has to be turned on before you actually get all those functionalities. So power supplies, positive or negative, are kind of like that. So basically, you can imagine this positive and negative power supply, the pins that provide power, the pins that provide electricity to your op-amp. That's why sometimes we don't show them, because, well, we imagine that they're there, right? It's connected to power supply, it's on, and now we want to actually analyze the op-amp. But then sometimes we actually show them because, well, their value is important. So sometimes it is important, and we're going to see why in a very short future. So in a few slides, we're going to see that why it is important that this voltage at this point, is it 5 volts, 10 volts, 15 volts? So sometimes that number is important, sometimes it's not. And you're going to see in the examples that basically when it is important and when it's not, right? But generally, you have 5 terminals, so 2 inputs. We have the positive input or non-inverting input. Sometimes we show it as in P, and then the negative one, so in N. We have the positive supply, V plus, and negative supply, V minus, and then we have the output. Okay. Another point to talk about is that when you purchase an IC, one of those black little packages that we saw before that I said they come in different sizes and shapes, you might actually get 1 or 2 or 4 op-amps inside that IC, or even more than that, right? So these are just 3 examples. So if you buy an IC with, like, I don't know, this is one example where you buy an IC, it has 8 different pins. So you can see that how the op-amp is actually connected. So basically, pin number 2 is connected to the inverting input or the negative input, 3 is connected to the positive input, and 6 is connected to the output. And then you can see that the positive supply is connected to 7 and negative supply is connected to 5. In this case, 1, 8, and 5 are connected to nothing. So it's a package that, well, those big metal pieces that you saw as pin, when you look at under the cap, when you look under the hood, when you scratch off the ceramic, you will see that, well, three of them are not connected to anything, and that's okay, right? It's just that, well, this is how the company is selling their product, right? But then you might actually see in some cases you have the company puts two op amps in one IC, right? So it's actually a nicer way if you need two amplifiers and you don't want to make your PCB, your board area, basically if you want to minimize the area of your board, well, this is one way to go, or even better than that would be this, right? So again, um, always there are two pins that are connected to the inputs, one pin connected to the output, and then, well, the same thing for the other guy. And then you can see that the supply, you only have one positive and one negative, not two positive and two negative. Why? Because, well, it's supply. You can actually connect it to both of them. Similar way that you might actually want to connect the power supply to two different circuits, right? If both of them need a 5 volt, why do I waste an extra pin on a 5 volt and bring 5 volt in two different pins, right? Same thing with the 4 op amps. So we might get op amps in different kind of packagings, and depending on what we want to do, we decide to go with one of the packagings or the other, right? These informations normally are available, not normally, always available in the data sheet of the IC.